Greetings, Professor Van here. This video discusses wireless connectivity for IoT devices. Numerous technologies exist to support IoT machine-to-machine applications. Many such implementations will entail wireless connectivity at the physical and MAC layer. Available wireless networks that can be utilized for IoT machine-to-machine applications include the following. Personal area networks or PANs, which includes Zigbee, Bluetooth, and near-field communications. Wireless local area networks or WLANs uses Wi-Fi. Metropolitan area networks or MANs are connected via WiMAX. And lastly, for global applications, satellite networks are employed. Don't get the wrong idea. IoT M2M connectivity might be achieved by wired means. For example, power line communications or PLC, base grid management, uses wired technology for connectivity. PAN or WPAN. A PAN, also called WPAN, is a network used for communication among intelligent devices physically close to a person. This includes smartphones, tablets, body monitors, and so on. PANs can be used to support wireless body area networks, also known as wireless medical body area networks, and or medical body area network systems. But they can also be used to support other applications. Medical applications include, among others, vital sign monitoring, respiration monitoring, electrocardiography, pH monitoring, glucose monitoring, disability assistance, muscle tension monitoring, and artificial limb support. Non-medical applications of WBANs include, among others, video streaming, data transfer, and entertainment and gaming. Non-medical applications of WBANs include, among others, video streaming, data transfer, entertainment, and gaming. The reach of a PAN is typically a few meters. The devices in question are sometimes known as short-range devices. PANs can be used for communication among the personnel themselves. This is known as intrapersonal communication, or for connecting to a higher level network such as the internet. The following network topologies are applicable to personal low-power radio networks. 1. Broadcast. This is an environment where a message is sent from a device in the hope that it is received by a receiver within the range. The broadcaster does not receive any signals back. Number 2. Mesh. Mesh is an environment where a message can be relayed from one point in a network to any other by hopping through multiple nodes. Next is the star. Star is an environment where a central device can communicate with a number of connected devices. Number 4 is scanning. Scanning is an environment where a scanning device is constantly in receive mode, waiting to pick up a signal from anything transmitting within range. And lastly, we have point-to-point. In this mode, a one-to-one connection exists, where only two devices are connected over the communications path. Zigbee and IEEE 802.15.4. As we have seen, the commercialization of consumer-based IoT services requires the introduction of wireless, low-power, battery-powered sensors and actuators in people's premises. Until recently, this space has been comprised of several physical and MAC-specific non-standardized protocol stacks that do not interoperate. Zigbee's focus has been aimed at the little devices such as little switches, thermostats, electricity meters, remote controls, as well as more complex sensor devices found in the healthcare, commercial building, and industrial automation sectors. IEEE 802.15.4 standard distinguishes devices based on their hardware complexity and capability. Accordingly, the standard defines two classes of physical devices, namely a fully functioned device, or FFD, and a reduced function device, or RFD. An FFD is equipped with the adequate resources and memory capacity to handle all the functionalities and features specified by the standard. It can, therefore, assume multiple network responsibilities. It can also communicate with any other network device. An RFD is a simple device that carries a reduced set of functionalities, for a lower cost and complexity, of course. It typically contains a physical interface to the wireless modem and executes the specified IEEE 802.15.4 MAC layer protocol. Furthermore, it can only associate and communicate with an FFD. Based on these physical device types, Zigbee defines a variety of logical device types. These logical devices are distinguished based on their physical capabilities and the role they play on the deployed network. There are three categories of logical devices. First is the network coordinator. This is an FFD device that is responsible for network establishment and control. The coordinator is responsible for choosing key parameters of the network configuration and for starting the network. It also stores information about the network and acts as the repository for security keys. Next is the router. This is also an FFD device. It supports the data routing functionality, including acting as an intermediate device to link different components of the network and forwarding messages between remote devices across multi-hop paths. A router can communicate with other routers and end devices. Lastly, we have the end devices. This is now an RFD device. It contains just enough functionality to communicate with its parent node, namely the network coordinator or a router. An end device does not have the capability to relay data messages to other end devices. Bluetooth and its low energy profile. Bluetooth is a WPAN technology based on IEEE 802.15.1. It is a specification for short-range wireless connectivity for portable personal devices. This includes computer peripherals. Bluetooth was initially developed by Ericsson in the late 1990s. The Bluetooth Special Interest Group, or SIG, made their specifications publicly available. Bluetooth is a short-range data exchange communication protocol widely used in cellular telephones, smartphones, tablets, and PDAs. It has a range of about 10 meters or a maximum of 100 meters with power boost. Bluetooth is designed for a small variety of tasks, such as synchronization, voice headsets, cell modem calls, and mouse and keyboard input. The Bluetooth specification defines a low-power, low-cost technology that provides a standardized platform for eliminating cables between mobile devices and facilitating connections between products. While the cost of Bluetooth equipment is significantly lower than the cost of WLAN, the transmission range of 10 meters or less and the data transfer rate of 12 Mbps or less in version 2.0 of the standard are often considered a drawback. BLE, originally known as YBRE, or Bluetooth Ultra Low Power, is a low-power subset to Bluetooth 4.0, with an entirely new protocol stack for rapid buildup of simple links. BLE is an alternative to the power management features that was introduced in Bluetooth 1.0 to 3.0. As part of the standard Bluetooth protocols, BLE is aimed at very low-power applications running off a coin cell. It is capable of reporting data from a sensor for up to a year from a small button battery without charging. Although the BLE data rate and radio range are lower than the same metrics in classic Bluetooth, the low power and long battery life make it suitable for short-range monitoring applications in medicine. BLE sensor devices are typically required to operate for many years without needing a new battery. They commonly use a coin cell, for example, the popular CR2032. The aim of the BLE technology is to enable power-sensitive devices to be permanently connected to the internet. NFC. NFC can be used for IoT M2M applications. It provides wireless connectivity, but it is not a W-band technology. NFC is a form of contactless communication between devices such as smartphones, tablets, and other devices. Contactless communication allows the user to simply wave the smartphone over an NFC-compatible device to send information without having the need to touch the devices together or go through multiple steps setting up a connectivity. NFC is an offshoot to radio frequency identification, with the exception that NFC is designed for use by devices within close proximity to each other. NFC utilizes electromagnetic radio fields, while technologies such as Bluetooth and Wi-Fi rely on radio transmissions. The technology behind NFC allows a device known as a reader, interrogator, or active device to create an electromagnetic field that interacts with another NFC-compatible device, or even just a small NFC tag that is holding the information the reader requires. Passive devices such as an NFC tag in smart posters store information and communicate with the reader. But these devices do not actively read other devices. Peer-to-peer communication through two active devices is also possible with NFC, allowing both devices to send and receive information. Three forms of NFC technology exist: Type A, Type B, and Felica. All three types are similar, but communicate in slightly different ways. To operate, the interrogator sends out a signal to the tag. If the devices are close enough to each other, the tag becomes powered by the interrogator's signal. Since the interrogator's signal powers the tag can be small in size and can function without any battery or power source of its own. The two devices create a high-frequency magnetic field between the loosely coupled coils in both the interrogating device and the NFC tag. Once this field is established, a connection is formed and the information can be passed between the interrogator and the tag. The interrogator sends the first message to the tag to find out what type of communication the tag uses, such as Type A or Type B. When the tag responds, the interrogator sends its first command in the appropriate specification. The tag receives the instruction and checks if it is valid. If not, nothing occurs. If it is a valid request, the tag then responds with the requested information. For sensitive transactions such as credit card payments, a secure communication channel is first established, and all information sent is encrypted. NFC tags function at half duplex. The interrogator functions at full duplex. Half duplex refers to a device that can only send or receive, but not both at once. Full duplex can do both simultaneously. An NFC tag can only receive or send a signal, while the interrogating device can receive a signal and at the same time, it can send a command. Devices using NFC may be active or passive. A passive device such as an NFC tag contains information that other devices can read, but not read any information itself. An example could be a poster or a commercial sign on a wall, where other devices can read the information, but the sign itself only transmits the stored information to authorized devices. Active devices can read information and send it. An active NFC device such as a smartphone is not only able to collect information from NFC tags, but it is also able to exchange information with other compatible phones or devices, and can even alter the information on the NFC tag if authorized to make such changes. As noted, NFC is limited to a distance of approximately 4 centimeters. Bluetooth does offer a longer signal range for connecting during data communication and transfers. NFC technology consumes little power when compared to a standard Bluetooth technology, but not when compared with BLE, which uses less power than NFC. Only when NFC has to power a passive, unpowered source such as an NFC tag does it require more power than a traditional Bluetooth transmission. Another benefit of NFC technology comes in its ease of use. Bluetooth requires users to manually set up connections between smartphones and takes several seconds. NFC connects automatically in a fraction of a second. Although users must be close to one another to use NFC technology, it is faster and easier to set up than a Bluetooth connection. That's it for wireless connectivity for IoT. The contents of this video is from the Chapter 6 of the book Building the Internet of Things with IPv6 and MIPv6. You may read the book for a detailed approach on the subject.